Here's a different type of Hess's law problem. Actually not different type, but a little more complicated. Adding one more step that we didn't have to do in the last problem. That was more basic. I would call this an advanced Hess's law problem. We're just going to jump right into it. I've written the equations here. Here are the enthalpies. And down here is the equation that we're trying to end up getting to. So let's start right in. We'll look for C2H2 in the final equation. And notice in the final equation we want it to be a product on the right-hand side of the equation. Here it's a reactant. So in order to make that be a product instead of a reactant, we are going to have to swap that equation around. So I'm just going to completely reverse it. The products become the reactants become the products, and I end up with 2 carbon dioxide plus water, it's a liquid, to produce C2H2, which is a gas, plus 5/2 oxygen gas. So this equation is no longer any good to us. It's dead to us. We have this new one. Now remember, what happens to the enthalpy whenever we do that is that the enthalpy, when we swap the equation around, the sign changes. So now our delta H1 is 1299.6 kilojoule instead of minus 1299.6 that we had originally written. So, taking care of C2H2. Let's look and see what's next. Well, we have carbon or hydrogen. Here's carbon. It's only in this equation, just like C2H2 or acetylene was only in that first equation. So we look at that carbon. That carbon's only in this equation. It's a reactant. It's on the left-hand side of the reaction arrow. And here in the equation we're trying to get to, it is on the left-hand side of the reaction arrow. So we don't have to touch that equation. It's going to be good as it is. What's the last thing? Hydrogen. Where do we find hydrogen in any of these 3 equations? Well, we've looked at this one so far and haven't done anything with it. We've looked at this one here. We reversed it to get this new equation. And all we're left is this one here with hydrogen. Hydrogen's here is a reactant. In the final equation, it is also a reactant. So we're good. We've got our 3 equations. Everything's on the correct side. And you might look at that and say, wait a second. You've got oxygen in 3 different equations. You haven't done anything with it. You've got water in 2 different equations and you haven't even thought about it. And the reason why is that we only worry about the things that are in one equation. If it's in multiple equations like the water or like the oxygen, well, if we work everything else out, the water and the oxygen will work themselves out as well. Okay? So just trust me on this one. We're going to leave those alone. We've taken care of the carbon, the hydrogen, and the acetylene, so we're good right now. Okay? Now, the thing that we didn't have to do in the basic problem was to balance, to make sure that when we add these 3 equations up, that we end up with this one, that we end up with the correct number of things in this one. So, let's take a look. Let's just start at the very first thing here, the carbon. There are 2 of them in this final equation. So when I add all the reactants up, I better end up with 2 carbons, okay? 2 carbon atoms. So the only equation that has carbon in it is this one right here. So we know we need to end up with 2 carbon atoms. I've only got 1 of them here. So when I add this up, I need to have 2 of them. So I am going to put a 2 in front of this carbon. And you might say to yourself, but you can't really stop there. How can you just multiply one thing in an equation times 2 and nothing else? And you would be right. I can't. I can't just stop there. If I multiply this carbon by 2, I've got to multiply the oxygen by 2, and I've got to multiply the carbon dioxide by 2, and I also have to take care of this enthalpy. I've got to multiply it by 2. So if I multiply an equation by something, I've got to multiply the enthalpy by that as well. Good. Good. So now, when we add these together, we've assured that we're going to end up with 2 carbon. Okay. How about hydrogen? Well, I've got 1 hydrogen molecule here. I've got 1 hydrogen molecule here, and this is the only equation that has hydrogen in it. So I don't need to balance that one at all. When I add them up, I should end up with 1 hydrogen. Now, what's left? Acetylene. We've got 1 acetylene molecule here. I've got 1 acetylene molecule here. Both products, in both cases, there are only 1 of them. They have a coefficient of 1. So when I add them together, I would end up with 1 acetylene molecule. Good there so far. Now, what's left? Well, I have ensured everything's in the correct side of the equation, correct side of the reaction arrow. Now I have made sure that everything's going to balance out. And I know you're probably thinking that oxygen and that water, what's going to happen to it? Don't worry, we'll figure it out. It'll work itself out. So I've done those 2 things. Now what's left is to add everything up. You know how I roll on this kind of stuff. I add it up. I actually write it out as if it's an addition problem, going back to grade school. So we're going to go ahead and add everything together here. So I've got my 2 carbon. I'm going to leave off the state symbols just in this case because I know that they're all correct. You can keep track of them as you go through, and sometimes it can be confusing. But at this point, we're sure that everything's going to work out in terms of the right state of matter. Okay, I've got 2 oxygen plus 1/2 oxygen. That would give me 2.5. Could have written that as 5/2 if I wanted to, but it's same as 2.5, 2 plus 1/2. So the oxygen's good. What's next? Hydrogen. I've got 1 hydrogen. That's good. I've got 2 carbon dioxide. That's good. And I've got 1 water. Now, how about the products? Well, I'm starting here. I've got my 2 carbon dioxide. I don't have any other to add to it. So 2 carbon dioxide. I've got 1 water. That's the only one. I'm going to jump down here. I've got C2H2 plus 5/2 oxygen. 5 divided by 2 is 2.5. Okay, now let's go through. Anything that's exactly the same on the left hand and the right hand, we can cross out. If we have 1 water on the left and 2 waters on the right, we can cross the water out on the left and 1 of the waters on the right. So, carbon's here, no carbon as a product. 2.5 oxygen here and 2.5 oxygen here. Cross out. 1 hydrogen here, none as a product. Leave it alone. 2 carbon dioxide here, 2 carbon dioxide there. Good. 1 water here, 1 water there. Cross out. What's left? Well, I've got my 2 carbon plus my hydrogen to produce C2H2. Notice this and this are exactly the same. We can be pretty sure that what we've done is correct. And notice what we've done. We've added these 3 together to get this. So now what do we do with the enthalpies to actually get the number? Well, we're going to add them together. We're going to multiply 2 times a minus 393.5, and we're going to add that to minus 285.8, and we're going to add that to 1299.6. And whenever you do that, you should end up with an enthalpy of 226.8 kilojoules. Okay? And that should be to the appropriate number of significant figures. Remember, this is not a counting, a time that we count and choose the smallest number. We look at the least significant place, And that's what we should end up with, is significant to the 10th of a kilojoule. So, a little bit more complicated Hess's law problem. Nothing that we can't handle by using our rules for looking at and evaluating and calculating enthalpies using Hess's law. It's exactly the same procedure, just a few more things that we have to worry about. So, a little bit more advanced Hess's law problem. Now you can try a few examples.